to get out of the house sometimes. My name's Allison Foudy. I'm really pleased to be part of the Hailey Public Library team, and joining me are Lahela Maxwell and Denon Strope, and they are the tech wizards behind the scenes. And after the presentation, oh, that sounds better, there will be time for questions. A very big thank you to our partners for this series, focusing on space and astronomy, the Idaho Dark Sky Alliance. Check out their table over there. Boise State University and Sawtooth Botanical Garden. We're really pleased to welcome tonight's speaker and performer, there's some music, Dr. Daniel Peluso. Dr. Peluso is an astronomer, I should say, and maybe an astrophysicist as well. Is that both? All the things. He's a researcher, he's an educator, and he's a media creator. He's also a musician and a singer-songwriter who performs under the pseudonym Conner Eko, and he will be sharing some of his music with us this evening. Following Dr. Peluso's talk, hopefully, there will be a stargazing event with local astronomers and Dr. Peluso at the Sawtooth Botanical Garden. We're going to do this, everybody do this, starting at 9:30. And there'll be a dark sky Q&A, so even if there's no stars to be seen, there will still be good conversation to be had. And you never know here, it could 10 minutes later, it could clear out, and we have these wonderful telescopes to help us see what we can see. Dr. Peluso has earned many post-secondary degrees, culminating in a PhD in astrophysics from the University of Southern Queensland. His work highlights the significant impact of citizen science on planetary research and education, including several peer-reviewed publications. As an educator, Peluso has taught in both colleges and high schools, and even co-authored a paper with high school students, and I'm going to let him talk more about that later. Before his academic journey, he spent years working in the music industry, developing and promoting artists, and I had to include these because it was really cool. Fall Out Boy, Wolfmother, Bon Jovi, Robert Plant, and Alison Krauss. So he's got some music background. He was on the radio, the local radio station this morning as well, if you happen to catch that. And his current project, Conner Eko, has received critical recognition and airtime. There's a quote from his website that I wanted to share with you. I think it sums up career goals nicely. My ultimate career goal is to work as a full-time singer-songwriter while remaining involved in STEAM education and finding innovative ways to merge the two to inspire humanity, which is a very admirable goal. So please join me in welcoming Dr. Dan Peluso.
Okay, all right. Thank you so much, Allison, for that wonderful introduction. Thank you, everyone here, for coming out this evening for the talk and a little bit of a performance, too. This is called Democratizing Astronomy and Indigenous Knowledge Through Music and Citizen Science. And as Allison said, I'm an astronomer. I'm also an educator and singer-songwriter. And I've kind of had all these different ideas, things that I'm passionate about through my life, from music and songwriting to being an educator, but also, being an astronomer. And I'm trying to find ways to kind of combine those into something that I'm pretty excited about, and I want to share those ideas with you, as well as some projects that are currently ongoing. This talk is inspired by a song that I wrote that was inspired by a project proposal that I submitted for the U.S. Fulbright program, which I was named a semifinalist for this year. And I'll talk a little bit more about that idea later if we have time. But the song is called Our Skies, and this talk and the song and vice versa are inspired by each other. And I want to start off just by playing the fully produced, almost fully produced, instrumental version, and then at the end I'll actually sing the song, just me and piano. And you'll see throughout the presentation as well some of the lyrics from the song, which are kind of guiding us through the story that I'm going to tell. So first we're just going to listen a little bit. So there's a global cast of musicians playing on this. Using this new type of service called Musiversal, where I can connect to studio musicians around the world. And we have a flute player from Portugal, a bassist from Brazil, a percussionist from Brazil, drummer from Portugal, and eventually I hope to add some Aboriginal musicians from Australia this summer whenever I go there to try to make some relationships down there. Okay, so one thing that I learned from doing my PhD in Australia was this idea of land acknowledgement, which I'm not sure if I really have seen this before, and it made me really interested in this idea of indigenous astronomy and Aboriginal astronomy, and learning about indigenous cultures around the world. So I actually wanted to begin this to start with the land acknowledgement as well. And with this, I just want to say that I am not an indigenous person, but I am an ally. And with that, I want to do the acknowledgement here that we honor and acknowledge and respect the traditional custodians and owners of this land. And forgive me for any mispronunciations, the Nui Shoshone, Numi Paiute, and the Penquate Bannock people, whose descendants are citizens of the Shoshone Bannock tribes of Fort Hall, the Shoshone Paiute tribes of Duck Valley, Fort McDermott Paiute Shoshone tribe, the Burns Paiute tribe, and the Confederated tribes of Warm Springs. And we also want to pay respect to all elders past and present, and any indigenous elders of other communities who may be here or watching online today or in the future. There's also this great idea in indigenous cultures about being oriented with where you're at. And I meant to do this before, but I guess is that the West? Where are we at? Yeah. Okay. So here we have the West, North, okay, South and East behind me here, and then but we also think about above. All right. So what's above our sky, and then what's below. So orienting yourself in your place is something that's really important too. All right, so in order to begin, I gotta tell a story, and I gotta go back a little bit, about 13.8 billion years, and I'm gonna play a sound for you to start that. So what you just heard is what's called a data sonification. Right? This is where we take data from, for example, scientific instruments, and we turn it into sound. We sonify it. Now, before I get into how that data was created and what that means, I want to introduce another idea of incorporating this type of idea with music. So about 12 years or so ago, I was in this band based in Pittsburgh, Pennsylvania called Falling Andes. That's me doing my rock slide. I don't know if my knees can handle it now. I'm not that old, but it looks painful. And this was an early attempt before I even did my PhD at mixing data sonification with a pop rock song. And I'm just gonna play. This is an unreleased song. Maybe one day I'll release it, a new rendition of it. But take a listen just to a little bit. Just a kind of a fun way to kind of do outreach, I think, and combine pop music and astronomy and data and science together to get people excited about what's going on with what we're learning about in space. Okay, so all right, so now the science of what's happening. What happened is about 13.8 billion years, beginning of the universe itself. We had basically the whole universe starting from a single point in time. And over the course of time, we had inflation, and we can actually pick up this light energy. It's called the cosmic microwave background radiation, with our telescopes. In fact, right now, you sitting here, you're actually getting hit by this microwave radiation. If you're, I was on the KDPI radio this morning, and it made me think, oh, I'm on the radio, but if we were to tune to, the static in between the channels, interlaced in that signal is actually evidence of the Big Bang itself, this cosmic microwave background radiation. Now, the sound that you heard comes from satellite measurements of this cosmic microwave background radiation, the oldest light in the universe. And in this graph here, this is actually showing the peaks of the temperature fluctuations from the early universe itself in that Big Bang. It's kind of like a pressure wave, sound waves. We hear a lot that there is no sound in space because sound needs a medium to travel through. But the early universe was so compressed and packed that there actually was sound there because everything was so compressed and close to each other. But we can take that telescope data and turn it into sound. This was created by an astronomer at the University of Washington by the name of John Kramer. I'll just play a little bit again too, now that you can kind of understand. You're literally hearing the first 760,000 years of our universe in just 20 seconds. Cosmic ripples, sound stretched and shifted for the expansion of space and time. Okay, so after that, we had stars forming and galaxies. Galaxies are a collection of stars, and one of those galaxies that formed was the Milky Way galaxy. That's our galaxy, our home. And about 5 or 6 billion years ago, there was a star that exploded. It's a supernova. And what happens when the stars explode is that they create the heavier elements on our periodic table, and they create these gas clouds called nebulae. This is a beautiful picture of a nebula. So like 5 or 6 billion years, there was a nebula, and a star formed in that nebula. These are star factories. These are the places where stars are formed. The circle of life, stars die, and then they're rebirthed in this cosmic cycle. And this is a picture of a baby solar system. It's not our solar system, but early on in our solar system, it might have looked something like this. This is at the center is the star of this baby solar system, and the concentric rings around that represent the carved out orbits of the planets forming in that system. So our solar system looked much like this in the past. This is an artist's rendition of what that may have looked like. And something very interesting happened on at least one of those planets, maybe more of them, we're still searching, and that's life. And the first evidence of life came about 3.5 to 4 billion years ago. It was simple, single cellular life, just microbes. And something happened that's kind of important to the history of life is our first mass extinction event. So a mass extinction event is where a large portion of life on the planet goes extinct. It turns out that over 99% of all life that's ever lived on this planet has gone extinct. And one of the first big mass extinctions happened when one of these microbes called cyanobacteria, one of the first photosynthesizers, so turning light into energy and exhaling oxygen. And that oxygen was very poisonous to all life on Earth at the time. So it caused this big mass extinction. And that was about 2.5 billion years ago. Now, this was good for us, bad for the anaerobic life at the time, because this led for more complex life to be able to evolve because of being able to metabolize things better with oxygen. This is 500 million years ago. We have the Cambrian explosion, and then we have the dinosaurs. We all love the dinos. Talk about dinosaurs in space, you get any kid excited, or dorky adult too. And something happened to dinosaurs, another mass extinction, got hit by a giant space rock. So this is 66 million years ago, another mass extinction. They call this the Cretaceous Paleogene extinction event. And astronomers, we like to make a joke out of this, that asteroids is nature's way of asking, how's that space program coming along? To give you an idea how big that rock was, so when I was flying here from San Francisco, I thought about this, and I looked out the window. Average cruising altitude of a commercial plane is about 33,000 feet, or 10 kilometers, or 6 miles. This impactor for the Chicxulub asteroid was about 10 kilometers, 6 miles in diameter. So if you imagine that just laying on top of the surface of the Earth, the airplane at cruising altitude would just skim the top of it. That's how big this rock was. Now we have evidence of this impact in the Yucatan Peninsula. This is a really cool graphic showing the perimeter of the crater for the Chicxulub craters in Mexico. And along that perimeter are these sinkholes, which are called cenotes. So if you ever go to Cancun or Tulum, Mexico, there's these beautiful sinkholes, as you can see in the image. They're wonderful to go swimming in and to explore. But these were actually created from the geological events from that asteroid impact 66 million years ago. And the Mayans, who are amazing astronomers, they used these as part of their spirituality and their system. What is above and below, thinking back to, I said, orienting ourselves with the direction in the sky. And we'll get a little bit more into that a little bit later, but this is a preview, I think, of what's to come, this asteroid impact, which then, let the dinosaurs go extinct, but then let humans to evolve. And this is an interesting bit, because there was a paper that I read about this idea that an ancient supernova, before Homo sapiens, before humans, may have actually sparked wildfires that inspired our hominid ancestors to leave the trees and to walk upright. An ancient star explosion that caused a wildfire that caused us to go and look up at the sky. Now, whether that's true or not, we have been looking up at the sky for a long time and wondering our place in it. And eventually we had humans, Homo sapiens. That's Latin for wise ape. One of the things, or some of the things that set us apart from other life on this planet, is our ability to walk upright. We also have this larger brain to mass ratio. However, actually ants have a bigger brain to mass ratio than us, but I think we might be smarter than ants, maybe. Our brains, though, use 20% of our body energy. If you think about our brains, they're very complex structures. There's somewhere between 200 and 400 billion stars in our Milky Way galaxy that we live in. It's estimated now that there's about 86 billion neurons in our brain. So almost as many stars as in our galaxy. But there's 100 trillion synaptic connections between those neurons, which is many more magnitudes than the amount of stars in our galaxy. We also created language, human language. This is really important for us to pass down our knowledge. Before, it was just genetics. My cat knows how to jump and hunt and do other things without thinking about it. When you eat an apple, you don't have to think about digesting it. Your DNA, your genetics tell you how to do that. But if you want to pass down knowledge, we need a knowledge system. Now, an interesting cosmic perspective to bring up is that if you look at the DNA of Homo sapiens, of our species, humans, and you compare that to chimpanzees, there's only a 2% difference between us. And chimpanzees are pretty smart, but again, we're a lot smarter than chimpanzees. We develop differential calculus and engineering and computers and technology. And I'm speaking to people from distant lands through a wireless electronic internet machine. So it's pretty amazing what we're able to do as a species. Now, if you imagine there's other life out there in the universe, and they had a 2% difference above us, what would they be able to do? It's an interesting thing to think about. Now, one of the ways that we had passed down knowledge for a long time for our species was through art and music. It was a knowledge system that we used for thousands of years. And before I talk more about that, I just want to point out these pictures here. At the top right is an ancient cave painting, I believe tens of thousands of years old. And although it does depict animals, and it was probably used in a hunt, there is new archaeological evidence showing that a lot of these ancient cave paintings actually are showing star constellations. So some of the dots you see around the eye of this animal and others that you can't see in the picture because it's cropped out actually represent constellations. And then below that, that's actually a computer model of the structure of our universe. However, it also kind of looks like brain cells. So inside of our head, we have this kind of mini universe. In fact, if you look up pictures of brain cells and you look up models of the structure of the universe, they have a very similar structure, which is kind of an interesting thing to think about. Now, knowledge systems are really important when we want to start talking about indigenous astronomy. Now, we're used to books in our Western culture, but before books, we had orality. So this idea of putting our knowledge down into books and uploading them now to the electronic internet, this is a relatively new thing to our species. Before this, we had to use orality. We had to pass down stories. And one thing that's important to understand is that when we think about indigenous knowledge, it's often looked at as just being myth and legend. And it's important to understand that that's kind of an abuse to, I think, the power and the knowledge systems that indigenous cultures have created. Because a myth is actually a way of transmitting knowledge. Mythology is the same as a book, but it's written in a different way. It's a different way of communicating it. There's very intricate and complex systems that were created by these societies, and they use story, song, dance, art, and ceremony in order to transmit those down through generations. And interesting to think about neuroscience today. There's a lot of research to show that music, dance, art, mnemonics are really important for helping us to remember things. Do you all know your ABC song? Or Happy Birthday? Or Twinkle Twinkle Little Star? So these are things that you learn as a youngster and carry through with you through your life. But ancient cultures would use this to tell stories. In order to remember them, we'd have to make them exciting and maybe include some spiritual or very extravagant stories just to remember the stories. All right, so here's the first lyric. Reads the heavens and the lands. So this is a picture that was a piece of artwork that was done by a Torres Strait Islander. If you're not sure where the Torres Strait is, this is just above the north part of Australia and below the south part of Papua New Guinea. And the Torres Strait Islanders, with the Aboriginal people of Australia, have a standing culture of 65,000 years. They're known as the longest standing culture in the world. And in the western Torres Strait, an astronomer is called the Zugabal Mabaig, which literally translates to star person. Very interesting person. They actually would go to a university quad, and they would study astronomy for 7 years, kind of like people who do a PhD. They'd become experts on a certain part of a field of astronomy. Now, in this picture, I just learned about this actually at a beautiful drive up from Boise this morning. It's such a beautiful land that you have here. And I was listening to a podcast, which I'm going to mention a little bit later. There's something else I learned in from it, where a researcher in Australia named Dwayne Hamaker was talking about what this painting means, this painting by David Boson. The stars on each hand, those represent the stars that this Zugabal Mabaig was studying. But then in the back, like that kind of hourglass shape, actually represents a drum. And this drum is how they shared knowledge. So they shared knowledge through music and song. And in the drum, the knowledge is actually coming out of the drum, showcasing them, passing down the knowledge through this art that they created. Now here's a great example of some of the amazing science that the Torres Strait Islander and the Zugabal Mabaig astronomers were able to do. This is a story about an eclipse. So they would have a ceremony, and in the ceremony, they would need to know whenever the attackers from a different tribe were going to come at them for this event that was going to happen. But it would only happen during a lunar eclipse. And the Zugabal Mabaig would need to predict when that eclipse would happen. And this is with no written language. This is all through this knowledge system of orality. And they were able to do this. Curious, raise a hand, how many people in here know exactly when the next lunar eclipse is? Yeah, and I'm not raising my hand either because I don't, and I have a PhD in astronomy. I have to look that up. So it's pretty amazing that they were able to do this just with their brains and their knowledge systems that they had. Unfortunately, no credit or acknowledgement in Western science texts are given to indigenous cultures that do not have a written language, that they were able to predict eclipses. And if you look at a lot of astronomy textbooks for like Astronomy 101, usually the section that talks about Stonehenge and maybe the Mayans is very short, but there's a very, very broad and rich history of indigenous astronomy throughout the world that we can learn a lot from, and it's really, really amazing. This is an example of a stone arrangement that is found in Australia with the Wurdi Yuang, and this is quite possibly one of the oldest astronomical observatories in the world. It's still being studied and debated, but it dates back about 11,000 years. This was used to tell when the summer solstice was. So the solstice occurs whenever Earth's poles have its maximum tilt towards the sun. The equinox is halfway in between those periods when the sun appears directly above the equator. And this particular stone arrangement showcases 11,000 years ago that they were tracking this. All right, so this is a fun one. This is called the celestial emu. So the emu is a native creature in Australia. I actually saw an emu in Australia. They're pretty tall and scary. My PhD advisor said to go up and pet it, and I was like, I'm not getting near this. I think it will kill me. They're beautiful creatures, though. They really are. And in Australia, in the southern hemisphere, you can actually see the shape of this emu. And they would use this emu to know when to collect emu eggs. And it's very well known across Australia that whenever the celestial emu is in a certain position in the sky, you know when and where to actually go look for the emu eggs. In order to get the emu eggs, they would go out in pairs, and they would use this emu caller. So I'm actually going to play just a little bit of this clip, and then I'm going to stop it.
So this is an emu caller, and this is used to lure the male from the nest, because the male is the one who minds the emu eggs. Even though the female lays them, the male is...
Okay, so as you can hear, it's a very percussive instrument. And as one person would play the emu caller, that would attract the emu to go away from the nest, and then the other person would come to collect the emu eggs, but they wouldn't take all the eggs. They would practice sustainability, and that's, I think, an important thing that we can learn, too, is this idea of sustainability. But I had an idea of the music idea that I'm trying to bring into, is, well, what if like we got these emu callers and maybe co-writing music with Aboriginal community members and astronomers, and we use those emu callers as a percussive instrument to create the beat for a song. That's something I'd like to explore. And then some other famous things from some other cultures real quick. This was made famous by late astronomer Carl Sagan, and using just sticks, feet, and brains, you can learn the size of the Earth and its non-flatness. So what happens here is basically using a stick located at the Tropic of Cancer, 23 degrees north of the equator. During a certain time of year, the solstice, there's going to be no shadows, or in a well there'd be no shadows. But then north of this, Eratosthenes, who was a famous astronomer during Greek time 2,000 years ago, was able to see a shadow there. So he paid somebody to walk down, and just using some basic trigonometry and geometry, was able to figure out the size of the Earth to be a little over 40,000 kilometers, which is only about 1% off from our true values that we know today. And you can actually do this experiment with students. I'm an educator. You just need some sticks, feet, and brain. However, you can use our modern technology to help you, so you don't have to pay someone to walk down many hundreds of miles to get the other measurement. So just something fun for your educators out there to take note of. And then I have to mention the Mayans, because I think this is one of the most amazing indigenous structures. This is Chichen Itza, which is also in Yucatan Peninsula. There's a lot of those cenote sinkholes around this area too. But at Chichen Itza, during the equinox, you see a slithering snake coming down the staircase, and It's amazing that the astronomers and engineers were able to actually build this structure, thousands of years ago in order to show that. Another one here, this is a petroglyph from the ancestral Puebloan civilization about 1,000 years ago. And this is an interesting one out of Chaco Canyon, New Mexico. And it depicts something pretty special. Also about 1,000 years ago, ancient Chinese astronomers noted in a star log in 1054 Common Era. Now, some people think, and this is still debated and being studied, that this petroglyph, as well as this star log, represent the same thing. And when we point our telescopes at that same object, this is what we see today. This is the Crab supernova remnant. So this is called SN 1054. This comes from a type 2 core collapse supernova, an ancient star explosion. So we have some ancient cultures that are actually documenting supernova early on in history. Now, I come back to the Aboriginal astronomers here, and this is a really, really cool story about fire magic. So in this Aboriginal story, Neruna is a hunter. He creates this fire magic with his right hand. And this is out of the red star we currently call Betelgeuse. And he's using this to chase the Pleiades, the Pleiades sisters, or also known as the Seven Sisters. That's off the screen. But he's blocked by Kumbudha, who counters her with her own fire magic from the star Aldebaran. Now, this oral tradition, this is a deep observation of the sky. Our star, Betelgeuse and Aldebaran, are both variable stars. So that means that their brightness actually changes over time. They get bright and dim. And this was recognized by Aboriginal astronomers long before Western science. So this is another lyric up here, became science before the Westerns. So this is a notable thing that Aboriginal astronomers discovered many, many years before Western science did. And this is another lyric. The song lines should be heard. These song lines are really interesting. These are basically taking what we learned from the sky, and country is really important to the Aboriginal people, and connecting what we learned from the sky to the land, and using this orality through music and actual songs to pass down this knowledge. Now back to that story of the fire magic. Now Yaruna's fire magic story actually has many versions, but they're all actually linked together through this very intricate song line across Australia. And the song lines actually, as I said, they connect the sky to the country for the system of knowledge. And it's a really beautiful, beautiful thing that they're able to do. I was hearing some stories where some Aboriginal peoples will actually be able to sing a song and know exactly what place that comes from. There's a deep connection between the sky, the land, and their knowledge system. This comes from a book called Songlines by Margot Neal and Lynn Kelly, and another lyric up here, In Danger of Forgotten. And that top quote comes from Aboriginal elder Mr. David Miller, who said, "You mob gotta help us. These song lines, they're all broken up now. You can help us put them back together again." And then the quote below by author Margot Neal, "The power of the song needs to be returned to country to keep it alive, or country will die, a bit like recharging batteries." So this beautiful knowledge system is in danger of being forgotten. And this is because of this threat that we have through colonization, past and both present, light pollution, cultural loss. And as we lose this connection to the stars, we're actually risking erasing both the ancient wisdom from these cultures and our shared human celestial experience. Anybody seen the movie Avatar before? This is in 2009, the highest grossing movie of all time. Over, let's see, $2.9 billion, $2.9 billion, the director James Cameron. Now, when I read this quote, this actually comes from the book Starry Messenger, Cosmic Perspectives on Civilization from Dr. Neil deGrasse Tyson. So in Avatar, sci-fi blockbuster that chronicles the plight of indigenous peoples on another star system, where they harness the mystical powers of plants and woodland creatures to defend their native planet against greedy corporate colonists. So it's an interesting thing to think of when we think about indigenous cultures and the atrocities that have happened to them, and we can relate that I think to this beautiful movie that James Cameron put together. So we're going to transition to my PhD work here and try to connect all this together, but I want to introduce this idea first called two-eyed seeing. So this comes from the Mi'kwawa language of Eastern Canada and Maine, developed by elders Dr. Albert Marshall and Merdina Marshall. And it's this idea of one eye using that indigenous knowledge system, and then the other eye comes from our Western science, and how they do not have to be mutually exclusive, but they can work together for mutual benefits for all. And a great example that I want to use to come back to the supernova remnants from the Crab Nebula that we talked about earlier. And we can imagine that if an indigenous culture in our archaeological findings had discovered some new star, which we call a nova, and then we were to point our telescopes up at this new star, we could then study that supernova remnant and learn quite a bit from it. This is an idea of two-eyed seeing. We can learn from these ancient cultures and then point our modern telescopes, using that knowledge that we learned from them in order to understand things better and work together. Okay, so astronomy and space science, this is something that's pretty special, I think, to us as humans. And as a teacher, anytime I bring up space and astronomy, students always get excited. They want to know about aliens. They want to know about space and planets. And I think it's something that's pretty common for our species to be curious about. And some consider it actually a gateway science. And we see this in our culture. We see it in our movies. So whether that's Star Wars or the Marvel movies, whether it's the newest news for an asteroid flying by that might hit Earth, or the front page of the New York Times. This is that image of the nebula that I showed earlier. This is from the James Webb Space Telescope. Or what about those UFOs? And then exoplanets. And exoplanets, that's actually a field that I focused on in my PhD. Exoplanets, these are just planets around other stars. And it's pretty amazing to think about is that on average, every star in our galaxy has at least one exoplanet around it, probably more. And I want you to think about this the next time that you look up at the stars. After the talk and performance tonight, hopefully if the weather permits, we're going to be going out doing some stargazing and using some telescopes. And when you look up at those stars tonight or any other night, just remember that you're not looking at just a star, you're looking at a star system of planets on it. Could that star right there have an exoplanet that has life on it? And could that life be intelligent? These are really interesting questions that I think a lot of us would be curious to know about. Now, one way that we find exoplanets is through what we call the transit method. And that's where we're just looking for a planet to be blocking out a portion of its parent star's light over time. So you can see in the animation here that as the planet transits in front of the star, that brightness dips. And we can detect that with our telescopes, and through various methods and follow-up observations, we can then confirm that it is an exoplanet. So before I started my PhD, I was an educator, and I wanted to get into a PhD program that would allow me to do astronomy and do actual science and study exoplanets, but also find ways to make astronomy more accessible. So I ended up doing this PhD. We're trying to make exoplanet science more accessible, and I use this network called the Unistellar Citizen Science Network, and that is a network of astronomers around the world using these telescopes, and I actually have one of them here. This is one of the telescopes from the Unistellar line of telescopes. It fits in a backpack. It's really easy to use. You just use your smartphone in order to connect to it. And the great thing about it is it has a digital camera inside of it, just like your phone has a digital camera. So we can actually save the pictures, and that's great to post on your Instagrams and your TikTok videos. But in addition to that, we can actually get that raw data from the sky. Astronomers, we like to collect data in this file format called FITS files. This is professional astronomical data files, and this telescope produces that. And we can actually use that to look at exoplanets, comets, supernova, these exploding stars, and we can perform this citizen science where anybody can use this telescope to contribute to professional astronomy. Now the map in the upper right-hand corner, that is showing the growth of the network from the time that I started my PhD until 2023. I'm not responsible for it growing that much. There's a whole team of people at the SETI Institute and Unistellar and a lot of amazing collaborators. But currently I hear that there's around 15,000 of these telescopes around the world. So what is citizen science? But this is also called participatory or community science. And the idea here is basically anybody can contribute. So because of the democratization of technology, we can now collect data a lot easier, and we have a lot of people with technology that can collect data like these telescopes. Now there's a lot of misconceptions about how an astronomer will actually work at a telescope. We're gonna, sit there in front of the eyepiece, or the astronauts in space are gonna go and look at the eyepiece on the Hubble Space Telescope. That's not how it works. So in reality, when professional modern astronomy is happening, we're doing this in front of a computer. And we're usually in a control room, and we're controlling the telescope remotely, and doing all kinds of different adjustments to how that telescope is getting our images and data. This is some images of of a professional telescope on the left from Lick Observatory, and then on the right is a citizen scientist telescope setup. Now notice how there's a lot of wires hanging out. There's a camera that has been connected to this telescope as well. I'm amazed by what citizen astronomers can do by setting up these types of instruments with all of these connections and digital telescopes and computers. But that is something most people won't do, is to do these intricate setups. So that's where I think new types of technology like these unistellar telescopes are pretty amazing. It's called a digital smart telescope. It does everything for you. It can collect the data. You don't have to connect all these wires to it. It's just kind of automatic. So it really does democratize our access to the night sky and our ability to contribute to science. So here's another lyric, is can our robots lend a hand? So I want to just highlight a few projects that I'm pretty proud of from my PhD work. And when you do a PhD, sometimes you do, an important part of your PhD is publishing work. I mean, when we're scientists, we need to publish our work. And I did a PhD thesis by publication. And my first author paper in a peer-reviewed journal was with the publications of the Astronomical Society of the Pacific. And this was on the Unistellar Exoplanet Campaign. And for this, we did follow-up observations for TESS exoplanets. These are exoplanets that a spacecraft called TESS, which is a NASA spacecraft that looks at exoplanets, observes. We had 163 citizen scientists from 21 different countries around the world contribute over 1,000 exoplanet observations. So in this, we showed that this network was capable of contributing meaningful data to exoplanet science. And we also showed in this paper that there was these inherent educational opportunities. And that brings me to my second paper, which was published last year. And this paper was for the discovery, for the confirmation for the discovery of a brand new exoplanet called TIC 139270665b. Just rolls off your tongue, doesn't it? So I like to call it the Lynx planet, or the cat planet, because it resides in the constellation Lynx. Now, the really exciting thing about this particular exoplanet in this paper is that we used this unistellar citizen science network in order to collect the data, collect some of the data for this. And I was involved in a program with the Chabot Space and Science Center in Oakland, California, where we had a very generous donation from the Gordon and Betty Moore Foundation to help us put some of these telescopes with students there. I worked with the students for months, teaching them how to use the telescope, teaching them about exoplanets, and I knew that there was going to become this opportunity where we could do an all-night observation to try to collect meaningful data, to try to find a transit of this exoplanet that we were trying to hunt down. So we planned it out. The students were really excited, and we stayed up all night. We played games. We watched movies. We played music. But then we also, of course, did the science, too. We set the telescopes up and had a lot of fun while doing it, while collecting this data. And all 16 of those high school students, as well as 27 non-student unistellar exoplanet observers, are co-authors on this paper. This paper was published in the Astronomical Journal. And that was a life-changing experience for a lot of these students and citizen scientists to be, involved in that project, but also to be published in real scientific work. So this is an amazing thing, again, another showcase of how we can democratize science with technology and programs. And students can learn by doing. This is just a picture of that array from the Chabot Space and Science Center, where we set up the telescopes outside. And I'll highlight another paper that's in peer review right now at the Journal of Science Teacher Education, where I showcase how we can use a new pedagogy way of teaching called modeling instruction to train teachers to do these programs with students where students are learning by doing. And that doing being this meaningful work of actually contributing to modern science, like using telescopes and collecting data, being involved in citizen science. And this exoplanet transit light curve that you see in the bottom right is for the exoplanet Cutter 1b. This was observed with one of the unistellar telescopes from one of my high school students last year. And this also helped with NASA's exoplanet program called Exoplanet Watch. So we can have teachers and students with no PhDs, no astronomy background being involved in professional astronomy work, doing astronomy just like professional scientists do. And I want to take a moment, since we are here in Idaho, and Boise State University and the Idaho Dark Sky Reserve helped arrange for me to be here. And I want to congratulate Rachel Huchmala and the entire Boise State University team, because I have this program in your state called the Telescopes for Teachers program, where they got a grant from NASA to place a lot of these unistellar telescopes with teachers throughout your state. And in July of 2025, so just this next month, that is being featured on the front cover of Sky and Telescope magazine. So make sure you pick up a copy and celebrate that, because it's pretty amazing. Now, a new project that I just started working on with some collaborators from my friends from the SETI Institute and Unistellar is a new company called SkyMapper. And SkyMapper is this new company which is creating a global network of autonomous telescopes. And this is to engage citizen scientists and local communities to monitor events, celestial events, and track satellites. It has a searchable database so that you can look up astronomical and satellite data. It has this continuous monitoring around the world. So one of the problems with our professional observatories is that if one goes down because of a problem or because of weather, then you're gonna miss that important information from that location. But if you have telescopes located all around the world, then you can mitigate that from those failures that you get from single telescope observing. So this is using cutting edge telescope technology like the unistellar telescopes, but also other telescopes that are gonna come online. And using that built-in community of the 15,000 plus telescopes around the world that we have access to. Now, the great thing that we're going to try to do with SkyMapper is expand this idea of a democratized new astronomy. We connect citizen science globally to observe the night sky. We want to empower communities around the world to participate in space sciences outside of these traditional academic or institutional barriers that have existed for a while. But also we want to do community-based observatories with indigenous partnerships. So the idea here is we want to build indigenous relationships and partner with indigenous communities in Canada and Alaska, Chile and Argentina, and Australia, Tasmania areas. And we'd like to integrate local knowledge from these communities, foster cultural engagement, build education programs, and also opportunities for Indigenous youth. And this will also help us to move forward this idea of two-eyed seeing, bridging the Western science with traditional Indigenous wisdom and knowledge systems. So we have this idea of new astronomy. If we think kind of like the history of Western science, astronomy was, a few astronomers, and we've grown over time. And it's kind of interesting to think back is that way back in time, actually, if you really think about Indigenous cultures, we kind of like all were astronomers in a way, and the most important people in the civilizations were the astronomers. They had the highest points in the hierarchy of these ancient civilizations. The astronomers were really important. The Zugabal Mabai were really important. But now with technology, we're getting blinded by the sky because of light pollution and other modern society distractions. But we also have this beautiful gift of technology that can make us all astronomers. So if we can have this two-eyed seeing, I think we can really move forward in this amazing way. And as we look out, I think we have to look back. This is Earthrise, taken in 1968 by the Apollo astronauts, spawned the environmental movement of the 1970s, the creation of the Environmental Protection Act. And it really makes us think about our home of planet Earth, and how we're all connected together. We're all here on this planet together. So another lyric, First Nations have wisdom. What is above is below. And this is a quote not from me, but from Jimi Hendrix, where I think he's known to have said, "Knowledge speaks, wisdom listens." So it's important that we listen to each other, and I think listen especially to the wealth of power and knowledge and beauty that we can learn from each other and our Indigenous cultures around the world. And again, as we look out, we have to look back, because we have some challenges that we're going to face as a society, that we face now and that we're going to continue to face in the future. This is Dr. David Grinspoon. He's an astrobiologist with NASA, and he has this idea of 4 kinds of planetary change. First one being random change. That's like when that asteroid impacted and wiped out the dinosaurs. Second one, biological change. That's like the cyanobacteria, those photosynthesizers that created the great oxygenation event in that mass extinction. The third one is called inadvertent change. So an example of that could be climate change. We didn't, I don't think, intended to disrupt our climate with the creation of our modern technology and the burning of fossil fuels. It was inadvertent. Intentional change would be, okay, we are going to intentionally do something. So that intentional thing could be, trying to decrease pollution, decrease light pollution, try to be more sustainable, work with more sustainable technology, decrease the impact of human-caused climate change. And we are part of the sky. That's another lyric, and in a moment I'm going to actually perform the song that this was all inspired by, and vice versa. So when these ancient stars exploded, they created the heavier elements on the periodic table, which created our star and our solar system and us. We are literally made out of star stuff. We're all connected to each other. We are the universe thinking about itself. The stars above are our ancestors, and that's also an important part of a lot of Indigenous cultures. So it's something for us to think about as we move forward. So what I'd like to turn to now is actually I'm going to go over to the piano, and I want to perform this song. It's called Our Skies. And I'm going to have the lyrics up here too, so you can follow along.
The songland should be heard
in danger of forgetting the knowledge of the stars was science before the westerns, and I hope we can see through their eyes. Oh, it's in our skies. The Zooga bag, a guardian of the stars, reads the heavens and the lands. Can our robots lend a hand? And I hope we can see through two eyes. Oh, it's in our skies. Oh, it's in our skies. Climate change, it's not natural. Electric lights blind our eyes. Satellites for profit, colonizing our skies. First Nations have wisdom. What is above is below. All humans are connected. We are part of the sky. We all live on planet Earth. Oh, we need our skies. Oh, we need our skies. Thank you. So this idea of the song came out from this Fulbright proposal that I told you about called Celestial Harmonies, Blending Modern Pop and Traditional Music to Share Aboriginal Sky Knowledge. And I got this idea of, I don't know exactly from where, but I was inspired from some different things. For example, Paul Simon's album Graceland. Paul Simon is a pretty well-known, famous American singer-songwriter who went to South Africa and created this beautiful art of combining traditional American singer-songwriting with this beautiful music of South Africa. So I thought, well, what if I could do a similar thing with Aboriginal people of Australia and the indigenous cultures there. And I'm actually also working with the University of Melbourne on possibly moving forward with a project where we could even combine data sonification and citizen science and these telescope programs that I talked about in the creation of music, both to encourage culture and share culture, and as a knowledge system, and bringing back that knowledge system that we use for the most of our existence and continue forward in a kind of new modern way. So that is the conclusion for now, and I just want to quickly thank Brian Jackson, Caitlin Austin, and Rachel Huchmala of the University of Boise State University, as well as the Central Idaho Dark Sky Reserve. I want to thank Carol Cole, Allison Foudy, and Lahela and Denon, and the Hailey Public Library, John Boydston of KDPI FM Ketchum, and then all of you for coming out, and anyone watching today, as well as our Indigenous knowledge holders. I would love feedback and collaboration and discussion with any Indigenous communities that hear this talk, so please get in touch. And if you would be interested in hearing the final version of Our Skies, I created a webpage here which you can scan with your phone on the QR code, and you can sign up to the email list. And I don't send too many emails because I'm really busy, but I promise to send one before it comes out, and you can keep up to date on that. And I plan to release that on August 8th. of this year. So thanks again for having me, and if we can stick around and have some questions and hopefully do some stargazing. Thank you. Sure. Yes. Sure. Oh, this one. Uh-huh. Sure, yeah. So the question is, you know, it's commonly understood that, you know, supernovas, you know, creating all the heavier elements on the periodic table, and, you know, we're all made of star stuff, but what about the fact that this periodic table says small stars and large stars and all this other stuff, right? So, you know, the devil's in the details, right? And so it turns out that the majority of our universe is made out of hydrogen and helium. This comes from the Big Bang itself. And then stars go through this whole life cycle, you know, through nuclear fusion. So our star, the sun, right now is creating energy through fusion by fusing hydrogen and hydrogen to make helium. But as our star and other stars progress through their life cycles, they're going to make heavier and heavier elements. And based off the size of the star, will depend on the highest element that they can make up. Now, for big, large stars, much larger than our sun, they will quote unquote go through the burning phase, the fusion phase, all the way up to the element iron. But that's the death element of a star. That's when it goes supernova. And then at that point, then it creates these heavier elements on the periodic table. But there's also cosmic rays that create them, and all the details of that I'm not actually familiar with. But it's you know, through the process of, you know, Big Bang and then the life cycle of stars and supernova that most of these elements come from. So they're pretty quick, but the brightness that happens can last like you know, weeks to months after a supernova happens. So you'll actually see this nova in the sky for a pretty long period of time, which is why it's probably been pretty recognizable by these ancient cultures. They would be so, for example, Betelgeuse, which we talked about earlier, if it were to go supernova, it would be so bright that you know, you'd probably be able to see it during the daytime, and it would be very noticeable by us. So when these things have happened in the past, it would have been very noticeable to ancient astronomers, indigenous cultures, which is why they would record them, and it would stay up in the sky for quite a long time. But then they do dim after a period of time. You know, it's and I can't remember the exact amount of time, but I think on average, like, you know, the brightest amount of it's about a month, and then it tails off from there. Mm-hmm. Yeah, so that was about 1,000 years ago, around. Yeah, so the question was the Chaco Canyon. So I'll go back to that if I can find it. Yeah, it's way, way back, right? There it is. Yeah, so the question so this was from 1,000 years ago. So this was discovered in a cave in the Chaco Canyon, New Mexico. So this is the indigenous Hopi community. And an interesting thing about this community is that Chaco was actually a center of academia, and people came from all over the world actually to go to this Chaco Center. This is a place where wisdom was shared from caretakers of Earth, and there's evidence from people of Central America, like the Mayans were actually visiting there, and people all over is this kind of like mecca of knowledge. And this was found in a cave near that kind of area, or near that area. So I don't know of other places besides the example that I mentioned from the star log from China, and then this is still debatable whether this actually represents the supernova. It could just be, you know, a star, or, possibly, a planet near, one of our planets near the moon when they created this, but that's still debatable amongst, archaeoastronomers. That's not my field, so I can't really speak too much more about that. But some people do think that this could be the same thing that the ancient Chinese astronomers observed to then, realize that this was the exploding star that created the Crab Nebula. Yeah, but I'm sure there's probably evidence around the world. Maybe we just don't know about it yet. And if they are known about, I'm not familiar personally. Mm-hmm. Any other questions? Yeah.
Imagine a classroom is fairly unconventional, which is sometimes a hard sell for administration.
Mm-hmm.
So is there a kind of model that you used, or where does that come from?
Yeah, so I actually want to go, so the question is, my classroom is probably very untraditional, so here, it would be easier if I go to the slide like this, and that it's usually problematic sometimes for administrators to let you do kind of more progressive ways of learning, and what kind of pedagogy do I use in the classroom, where does it all come from? So this is best explained, I think, through this whiteboard that you can see on the bottom part of this graphic or this slide. So there's a pedagogy called modeling instruction, and this was developed in the 80s and 90s by a physicist out of Arizona State University and a high school physics teacher. And they realized that how we teach physics is not very, very good. So they wanted to come up with a better system. And they developed the system called modeling instruction. And the idea here is that we can take the main models in a discipline and try to construct and deconstruct and reconstruct this model based off of observation. So instead of the teacher being the sage on the stage, the teacher becomes the guide on the side and then guides the students through these inquiry-based activities using actual data in order to develop the models around the discipline. So it can be a little bit more of a chaotic classroom compared to what an administrator might like to see, because your traditional classroom that you're traditional, and I say traditional because this is not the case with all like schools and all administrators, but what our traditional education system, sometimes portrays things as a teacher talking and the students are obediently being quiet and not saying anything, whereas a modeling classroom it's much louder, it's more interactive. Students are sitting around this whiteboard, they're running experiments, they're collaborating with each other. It's much more engaging than your traditional classroom. And there's been over 20 years of National Science Foundation support for this pedagogy, and there's a lot of research papers that show that this way of learning is very successful. So I didn't have too much trouble getting my administrators to buy into it, and there's I think there's 10 to 15,000 modelers in the U.S. and some around the world as well. So it's a pretty well-known pedagogical tool that was initially used just for physics, but a part of my PhD was trying to do the first research for it around astronomy. So in the whiteboard that is showcased on the slide, this was an exciting project that I did where one of the scientists that I worked with through the Unistellar Network, Ariel Greykowski, Dr. Greykowski studies comets. So we use this Unistellar telescope program to crowdsource data on comets. And she got us the data from the network and actually zoomed in to our class and talked to the students. And the students used the program to do photometry, to measure the light as it changed when this comet was orbiting around the sun. And we actually measure the difference in brightness from this comet. And they were able to model the orbit of the comet using this whiteboard and the program that we used on the computer using the data that the scientists provided. So this is literally creating a model of the comet's orbit around our sun, and that's how kind of a modeling classroom works. But it's much more engaging and it's a lot of fun, and they're doing real science, so it's learning by doing. Yeah, another question? Yeah. So just for everyone online and for the recording, the question was, the comment was that there, from the telescope program through Boise State University that Rachel runs, is that there are at least 2 telescopes near here. Would you say it was Sage? Sage School and Wood River High School, and then you said Stanley? Okay. So so teachers, get in contact with us, and so we can help you do citizen science programs. Also, please be encouraged to check out the American Modeling Teachers Association, or AMTA. That's the nonprofit that curates the modeling instruction pedagogy, and for the past 3 or 4 years, we've been running a modeling course that I helped co-design called Astronomy Modeling with Exoplanets. And hopefully it will run again next year. Maybe some of these teachers can take it, but there's also a lot of good webinars and workshops that are online. I've done some recently with Rubin Observatory, where we've talked about modeling. I know those are publicly available, so if you search up Rubin Observatory, you can get a little taste, a little appetizer of what modeling is like by watching some of those online. But I would also love to work with those teachers too. They're welcome to contact me. Other questions? All right. Thanks, everybody.